Alright, good morning. We will have a little organization of what we will get done today. I need to finish the lecture yesterday. Plus, there were some APA questions that I wanted to also do. Looking at my example, we need... Nope. I want to perhaps attempt just this question, or I could try and attempt this question. I might do that, question 8, at the very least. Then finish off that lecture before doing a Leetcode problem, and then I want to do a tutorial slide, set of tutorial slides for APA. We can kind of delete this area now. CS is done. Nafi, hello. Early stream today? Yeah, I mean early by 10 minutes usually. I mean this is 8:54. Just around, you know? Just around. Slightly earlier, yes, though. Okay. Then perhaps, you know, this Leetcode could reach us to lunchtime, to which I also need to go to the gym. And then by the time I'm back, I should also have a shower. I should be able to spend time on tutorial slides. Now it depends on what tutorial slides I want to do. And lecture 2, week 11 would be what we finally finish off with. It's still daylight out here in Canada. Usually I watch a stream around nighttime, around 9 p.m. I see. Still daylight. I'm guessing what? It's still around like 5, 6 p.m. Perhaps. Hmm. 6 p.m. Okay. Well, let us try and do this problem. Question 8. So, MDPs and reinforcement learning. The following. Okay, so move this. Cool. The following questions refer to this example. Imagine a kitchen robot whose task is to ask the user what kind of cereal he or she wants for breakfast. Wait for the answer and then hand out the appropriate cereal box once it knows the desired cereal. We want to design a simple dialogue system to handle the interaction with the user. A simple way to model it is via a discount reward Markov decision process with 2 states. Unknown cereal, where the robot does not know what cereal to give, and known cereal, where the robot knows the cereal to hand out. There are only 2 possible actions in the model. Action is ask cereal type and to give cereal. So ask cereal type corresponds to the robot asking the user for the cereal box he or she wants to have. The action is only available in state unknown serial and has a reward of -1. Okay. In that state. The probability of reaching state known serial is 0.8 if the user answers the robot's question, and otherwise probability of 0.2, the robot remains in unknown serial, if the user ignores the question or provides an unclear answer. Action give serial corresponds to the robot physically giving the serial to the user. The action is available in the state known serial and has a reward of 5. When the robot executes the action in state known serial, the Markov decision process reaches an absorbing goal state and finishes. As such, there is no action or reward available for this absorbing goal state. When the robot executes this action in the unknown serial state, the MDP reaches the absorbing goal state with probability of 0.3. It gets lucky and hands the right serial and receives a reward of 5. Or the person rejects the serial and the robot goes back to the unknown serial state with probability of 0.7 and receives a reward of -2. Given the reward, the value function that you calculate above, what policy would maximize the robot's expected reward? So given the value function that you calculate above, right? So the value function here, this is going to be something interesting. What policy would maximize the robot's expected reward? It's a good question. Now, what do you expect out of a policy to be given here? Like, is a policy a table? So that's something to consider. And in your own words, explain the difference between value iteration and policy iteration. Right, so value iteration and policy iteration is just literally understanding the concepts of those two. The robot designers are finding that the owner of the robots are demanding a refund because the robots get their serial preference wrong too often. Give one technique that the robot designers could do to improve the situation. Okay, that's interesting. Give one technique. To improve the situation. And imagine a reinforcement learning algorithm that monitors heartbeat information from a fitness device, such as a Fitbit, to determine whether a person develops a heart problem, such as an irregular heartbeat or a faster heartbeat. List one potential ethical dilemma that could occur in such a situation. Justify why you believe this could be a serious problem. Now, I feel like I could answer this one just out of my own understanding, right? Just think about it, right? Okay, so imagine a reinforcement learning algorithm that monitors heartbeats. List one potential ethical dilemma that could occur in such a situation. I don't know, person may become too dependent on the Fitbit. Person may, Fitbit may produce too many false positives, which leads to more loss of trust. For the product, maybe? One way to think about it, I guess. Anyway, there's two ways to think about this. I think those are right. Okay, well, that's more than enough questions that I've understood at the moment. Now, guys, there is one thing that I'm thinking of, which is this article. Now, this is a newsletter by James Clear every Thursday. And I love reading some of this stuff just because it's quite useful, I think. But we're going to read this now. So 3, 2, 1 on impressing others, the power of the mind, and the hidden costs of success. 3 ideas from James Clear. Number 1, focus on what provides value to others, not what impresses others. Other people spend about as much time thinking about your lifestyle and accomplishments as you spend thinking about their lifestyle and accomplishments, which is to say, not much time at all. The things we do to impress others rarely impress them for longer than 5 minutes, but the things we do to provide value for others can last a lifetime. In the long run, one of the most impressive things you can do is provide exceptional value. I agree. Number 2. Anger is like an oven. Heat without light. Heat without light. Okay, right. Forgiveness is like the moon. Light without heat. Right. Okay, fair enough. Number 3. If you look for evidence that people are conspiring to hold you back and the world is working against you, then it will take you no time at all to find precisely that. If you expect to encounter helpful people and experience a world that is working with you, then you will find plenty of evidence to support that view as well. The raw material for a sweet life or a bitter life is always there. The story you emphasize is the one you notice. Thinking of the glass as half full or half empty, you know what I mean? Alright, 2 quotes from others. Number 1, poet and novelist Ben Okri on the power of the mind. Beware the stories you read or tell. Subtly at night beneath the waters of consciousness, they are altering your world. I can understand that in the sense you don't want to say things which are negative because they will alter your world when you sleep. You can think about it that way, I guess. Hello, Ritesh. Number 2, Dutch watchmaker and writer Corrie ten Boom on worry. Worry does not empty tomorrow of its sorrow. Worry does not empty tomorrow of its sorrow. It empties today of its strength. Yeah, okay. Fair enough. One question for you. Think about someone who has the results you want or a lifestyle you admire. It's easy to want the results. What are the costs and trade-offs of their lifestyle that you may be overlooking? Well, that's a good one. I can think of someone right now. What I could be overlooking the amount of work that you may end up doing. And that's fine. I actually prefer doing the work. Now, at this point, I'm speaking to myself, by the way, guys. So don't mind me. But Yeah. Maybe I overlook the day-to-day, but I don't know. I think I have a good view on how the day-to-day could work. Okay, regardless. On omnivore shutting down, cool. Now, we can finish off this or do a Leetcode problem. I might do a Leetcode problem now. Now let's update Firefox first. Is it updated? I can't tell. No, I don't know. I'm guessing if I just quit and reopen, that'd be fine. Okay, there's the update. Okay. First off, let's do a monkey type. Ooh. Oh. Hmm. Okay. I have a challenge for you. What are the special symbols associated with each number from 1 to 9 on the keyboard? Try this without looking. Okay, yeah. So without looking, I don't think I know. Damn, I wouldn't know. Maybe 7 is the and percent. The 9 is the underscore. The 1, the 2. No, I don't even know. I don't even know. Because what, there's there's an asterisk. If I can maybe think about what the asterisk is. I'm guessing asterisk is like 8. I'm guessing a caret symbol is like... Nah, like a 5. I don't even know. Okay, a caret symbol is 6. Ampersand is 7. Star is 8. Alright, I was wrong about 9. So 9 is just open braces and then close braces for 0. I mean... yeah, Vim motions. I mean, here's the thing, right? You know, I remember the caret symbol and the star symbol, 6 and 8, as going to the left side and on the right side of a line. But then, oh yeah, the other one. Wait, isn't it 4? 4 is for the $sign, right? $sign is on the right side, I think, right? Let me see. Yeah, so it's $sign for the right side, caret for the left. Which is still a little bit confusing. And the only reason why I know this is because, well, using this keyboard. Tough question. Yeah, how do I undo? Escape. Okay, tab. Tab. Linked list. Whoops. Else. Ooh. Ooh. A. Not bad. Alright. Alright. Try problem or another backtracking problem? I think I'll go with another backtracking problem. Okay. Alright. Let's open this problem up also in its own Leetcode problem. And I just got to double check that it's just similar. Okay, so I mean, I'll read it from here first. Given a string contains digits 2 to 9, inclusive, return all possible letter combinations that the number could represent. Return the answer in any order. A mapping of digits to letters. just like the one on the telephone buttons is given below. Note that 1 does not map to any letters. Right. And so the input of digits 2 and 3, A, D, A, E, A, F, D, B, D, B, E, B, F, C, D, C, E, and C, F. Wow. Interesting. I might be fooling myself, but I feel like this problem is going to be okay. Right, now if you got 3 and 4, DE or DG, EG, or DH, DI, EG, EHEI, FG, FH, FI. Surely this is a pretty simple problem to solve, right? Maybe you'd have the mapping of digits. That might be something new, but you have a constructor, you define backtrack, which is just going to be a DFS, so I might just maybe call it DFS, fine. Return something, DFS of the digits, return the result. We're going to need a map, yes, yeah, so I guess then let's build out the map. So how would we want this? You know, each digit has its own value. We just use a hash table. It's probably best. Digit to letter. Digit to letter. Zero. 2. You can have an integer as a key, right? I think you can. Shouldn't be a problem. And then you have ABC. Now they're all lowercase, so maybe I'll just go strings ABC. Alright, don't worry about things too much. DEF 4, GHI 5, JKL 6, something something, yank the full line, paste, 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 replace with 7, replace with 7, replace with 8, replace with 9, JKL, MNO, PQRS, TUV, WXYZ. Okay. Integers may be an issue when we backtrack. Okay. We'll see when we get to it, alright? We'll see when we get to it. Because at the moment I don't see the issue. yet. So maybe I'll say index. I guess the digits is a string at the moment, right? So calling it integers is actually probably not a good thing. So if we do just say the characters, right? Let's say, yeah, I think that actually you're right. I might just make them actual characters. If only I knew a macro that could do this, but I haven't learned about how to add macros to Vim yet. So, rip me. Okay, DFS something where we're going to have another DFS inside within a for loop for letter in a digit to letter of the specific digit of interest, right? We might call it D, or digits I could be the digit of interest. Then you do the DFS, for that letter. For that number. So I might get rid of that. So for that number. Thing is, like, what do I want to return here? What do I want to have here? So if you reach the end, if is equal to the length of digits res.append constructor.copy. So that would be the base case. But if that I isn't there yet, then yeah, so a letter in digits to letter, let's see. You need to constructor dot append the letter constructor dot pop DFS of I plus 1. I need to think of this. So say if you have Lucas, correctness of rev. Oh yeah. Thanks for letting me know. That looks complex. Why does this look somewhat can I even understand this? Xs, x is 0, possibly maps to y's epsilon. Y is equal to, yeah, no, I'm not following that expression, but not bad. Not bad. Correctness of rev, which I'm guessing stands for reverse, right? It is this, a linear time imperative implementation of reverse of sequences that are, yeah, so an imperative implementation that are implemented as singly linked lists that can achieve via a loop with the following program. I see. So this is related to, say, are you doing this in Haskell, perhaps? You know, that's Haskell or Prolog, because I've been through that. I think I've seen something similar for the reverse of a linked list. So, or reversing a list. So it's a recursive approach, right? Should be. I'm not reading into it, but I kind of know what you're talking about. All right. Okay, so thinking about it this way. So DFS, you start from 0. If I reaches the len of digits, then you know to append this and then you would return. Now, if you're not at the end yet, you look at the letter for the digit. So digits I. And then you would add that letter and then do a DFS. And then you would pop that letter afterwards, after you've done that DFS. And I'm constructing, say this is constructing a string. So I could perhaps say constructor, when you copy, you join. So dot join. That might be accepted one test case, so that's good. Second test case, output fails. Okay. Let you get back to it, but we just do proofs with proof structures and theorems like non-empty sequence decomposition, what you probably already did a while ago, I assume. To be honest, this is not memorable to me. I can't recall. I can't recall this. You can tell where my brain's at with that type of stuff. But nonetheless, like, still good to learn all that stuff, you know? Even if I forget it all. I think also the thing is proofs have, I need to understand proofs better, personally. Like, it's a weakness of mine, to some extent. So, in the case where your digits is empty, you just want to return Oh, there's gonna be something else, is there? No! Wow, okay, well that was super easy. That took not long at all, really, to solve that one. Let's watch the solution though. So it was as easy as I anticipated. Whoops. Like I didn't even have to write an Obsidian note for this. Let me actually move this. Backtracking. I guess you could say you use a hash map. Yeah, not bad. This problem was pretty straightforward. What's up with that? The statistics on Leetcode just like have gone to shits. In sub 10 minutes, I will say. Alright, good. Oh, that was pretty easy. I won't overstep my boundaries though. And move to a next question, another question. Will I? It's pretty tempting. It's pretty tempting, what can I say? But let's have a look at, say, just the solution. Backtrack. Current string is equal to digits. For sure.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve letter combinations of a phone number. So we're given a string of digits that contain only 2 through 9. So the digits are only going to contain the numbers 2 through 9. And we want to return all possible letter combinations that the number could represent. And so basically what this problem is about is like when you wanted to text people with old phones, you only had these digits, right? So in order to have characters, you'd map a number like 2 to the characters A, B, C. And you can see the reason we're doing 2 through 9 is because 1 was not mapped to any digits, right? So we don't need to consider the 1. 2 was mapped to ABC. 3 was mapped to D, E, F. Basically each number or each digit, 4, 5, 6, each one was mapped to 3 characters. Some were mapped to 4 characters. 7 is mapped to 4. 9 is mapped to 4 different characters. So then if you're given a string of digits, let's say 2, 3 in this case, right? 2, 3 is our string.
So
how many different
where is your internship going to be?
We have here? You can see we have a
It's going
bunch,
to be in
right?
Sydney.
We have 9 different strings. Why do we have 9 different strings? Because this 2 could be 3 different characters. It could be A, B, or C. This 3 could also be 3 different characters, D, E, F. So 3 times 3 is 9. So basically we can have 9 different combinations of these characters, right? We could have A, D, we could have A, E, we could have A, F, right? And so on, right? So we could have B, E, B, BF, and then do the same thing for C, right? So then we'd have 9 different strings. And so basically you can tell that this problem, right, like writing out the solution like this, it's not that difficult because we're gonna basically be forced to brute force this problem, and it's a backtracking problem because we have to brute force it, right? We have to basically find every single combination that we could get using the given digits. And you might have noticed I've been doing a lot of backtracking problems recently, and that just goes to show you that backtracking is a very important algorithm. So let me just show you kind of the drawing of the backtracking solution. So luckily for us in this case, we're only given 2, 3, right? And so
let me think about, say, just the time and space complexity. It's 3 to the power of n, where n is the length of the string, I think. Approx 3 or 4 to the power of n. Yeah. Right? So it's like roughly 3.5, I guess you can say, but it's not really because statistically, statistically, doesn't matter. Awesome, how old are you? I'm 21. So technically, like, yeah, people who are in second year are doing this internship, probably, but I'm in my master's.
Only need to find, okay, 2 maps to these 3 characters, 3 maps to these 3 characters, but we know in total, it's possible we could have a 4, we could have a 5. If we had a 4, we know 4 maps to the next 3 characters after this, so G, H, I think, unless I'm forgetting something. And basically, we could have any character, right, from 2 through 9, so we're going to need to create a hash map or some kind of way to map every character from, or basically every digit from 2 all the way to 5, 6, 7, all the way to 9, right? And map them to the characters that they end up being, right? We know 9 is, I think, going to be X, Y, Z. We're basically going to have to hard code this map of characters. There's not like a clean way to do it, mainly because some of the characters, I think 7 has 4 characters, right? 7 is mapped to 4 different characters, and so whatever. But this is a pretty small hash map, right? So it's not a big deal if we have to hard code it. But now let's just look at this problem itself. How are we going to solve it? Well, so the first character is 2, right? So 2
I think I can speed this a bit.
3 different characters. So 2 being the first digit, it can map to A, B, or C, right? And the next character we know, or the next digit, is 3. So from A, we could have 3 different characters that follow after it. We could have a D, we could have an E, or we could have an F. And that's going to be true for every single one of these, right? We could basically put a D, E, F after each of them. And this is the entire backtracking tree. So based on this, what's our solution? Because remember, we want to know the strings that this could map to. Well, this is one string, this is one string, this is another string. So basically for each of the leaf nodes in this tree, we're going to follow the entire list of characters that came before. That's going to be the output strings, right? AD, AE, AF, and so on, right? BD, BE, BF, and the exact same thing for C. So when you visualize it like this is actually a pretty simple problem. So now you just need to know how to write this backtracking algorithm, and I'm going to show you how to do this recursively. But before I do that, the time complexity for this is basically the number of combinations that we're going to have. So the question is, how many different outputs could we have for a string? Let's say the input string is length n. How many different outputs could we have? Well, since we know that there's some characters, like I think 9 maps to 4 different characters, I think W, X, Y, Z actually. So the brute force is going to be 4 to the power of n. That's how many outputs we could actually have, right? Because maybe we get a string s equal 9999, right? So basically we'd have 4 choices for each of those characters. So 4 times 4, basically 4 to the power of n, which is the length of the input string, right? So that's the number of output strings that we're going to have, and the length of each output string is going to be the same as the length of the input string, right? So really, the time complexity is going to be big O of n times 4 to the n. And basically, this is the worst case time complexity. Okay, so now let's get into the code, which is going to be fairly short. So the first thing we want to do is have a result. This result is
So look, he says 4 times 4n, so n times 4 to the power of n.
Puts we could actually have, right? Because maybe we get a string s equal 9999, right? So basically we'd have 4 choices for each of those characters. So 4 times 4, basically 4 to the power of n, which is the length of the input string, right? So that's the number of output strings that we're going to have, and the length of each output string is going to be the same as the length of the input string, right? So really, the time complexity is going to be big O of n times 4 to be the same as the length of the input string, right? So really, the time complexity is going to be big O of n times 4 to the n. And basically, this is the worst case time complexity of output strings that we're going to have, and the length of each output string is going to be the same as the length of the input string, right? So really, the time complexity is going to be big O of n times 4 to the n. And basically, this is the worst case time complexity. Of n, which is the length of the input string, right? So that's the number of output strings that we're going to have, and the length of each output string is going to be the same as the length of the input string, right? So really, the time complexity is going to be big.
I suppose I get that. 4 to the n is actually just the number of leaf nodes times by n.
O of n times 4 to the n. And basically, this is the worst case time complexity. Okay, so now let's get into the code, which is going to be fairly short. So the first thing we want to do is have a result. This result is going to contain the combination strings that we're trying to build. And the next thing we want to do is create a map of digits, right? We want to take every single input digit that could be possible, like 2, and map it to the characters that are possible. So A, B, C, right, for 2. And unless you want me to type this out, I think I'm just going to copy and paste it. So this is what our digit map is going to be like. And you can verify this if you have an old phone laying around, that this is the correct mapping from digits to the following string characters. So now let's write that backtracking function. It's going to be a recursive function, and I'm going to declare this function inside of this function so that we don't need to pass in these parameters every time we call this backtracking function. And we also don't need to pass the digits that we're we're on, I'm only going to pass in one variable I, which is going to tell us what index we're at in the digit string that we're given as the input to our function. And I'm actually going to pass in one more variable, so the current string, meaning basically the current string that we're building. So let's say our input was 1, 2, 3, and the current string would contain something like A, right? So if we've only visited 1 so far, we'd have A, and then we'd want the next two characters from 2 and 3. So we know the base case is if I is greater than or equal to the length of digits. Or actually, an even better base case would be our current string. Let's say the length of the current string is exactly equal to the length of digits. That means that we've basically been able to take every single digit and then map it to a character, because current string is going to contain those characters. And if that is the case, then we are allowed to take our result and add to it the current string that we just built. And then since this is the base case, after that we can just return. If this is not true though, that means we haven't finished building the current string. That means we need to continue going through the digit that we're at, right, at index I. So let's create a loop to do that. So basically I'm gonna take digits of I. That's gonna tell us the current digit that we're at, right? And I wanna take this digit that we're at and I wanna map it to the list of characters that it maps to, right? So if we had 9, we know 9 maps to W, X, Y, Z. So how can I do that? Well, that's why we created this digit to character map. We can take a digit and then map it to a character. So digit to character, I'm gonna take this digit, and now basically this is going to be that string that it maps to. And I wanna just go through every character in this string. So for every single character in this string, I wanna brute force this, right? So for every single character, I'm just gonna call backtrack. I'm gonna make that recursive call, right? So for I, we're gonna increment I by 1 because we're moving to the next digit. And for the current string, we're gonna just take the current string that we were given and add one more character to it, the character that we're currently visiting, C. And that's actually all that we have to do. We have our single base case and we have our recursive case. You can see that the only thing that might be different for you is that our recursive call is inside of a loop. So with this backtracking function complete, now let's actually call this backtracking function. So the parameters to give it are gonna be 0 for the index, and the current string is initially just gonna be empty, right? But I'm actually gonna need to make one last modification. So we're only gonna need to call backtracking if the digit string that we're given is non-empty. And the reason is because if digits was empty, then our recursive call would be called, and then we'd execute the base case once. So then we'd end up returning this as our result. We'd add the empty string to result. But in the way this problem is defined, if digits was empty like this, if digits was just an empty string, the output that they actually want is just an empty array like this. So that's why we have to put this inside of a condition. But other than that, all we have to do is now return our result, and the function is complete. So you can see that it's pretty efficient, about as efficient as you can make a problem like this, even though it's a it's what's it called? It's an exponential function, right? But I
agree with that. Anyway, so it's fine. Submission submitted. We can put a pin on this for today, I think. Would there be... Do I want to do one more? Nah, I won't. I won't do one more. However, you know, looking at all of these, they're pretty cool. It's nice that I've done all of these already. It's pretty nice that I've done all of this already. It's very nice to see. Almost as if, you know, I want to slowly sparse out. Sparsely complete some of these as well. Especially greedy. Like these types of problems I need to do more of. And I really want to do more of. But we'll call it that for now. This was pretty simple. Leetcode done. Gonna finish watching that lecture. It's gotta be this one, I think. Yep. Hello, Shah. Welcome, man.
Using something like RCNN, actually it was YOLO, but it's been trained on a bunch of classes. Now we have to train it to identify the things that we want it to find. And so the question is, how well does it generalize, and is it able to adapt to, transfer its learning to a set of classes that are outside its training set? Cool.
Object detection now.
Moving swiftly on. Object detection. So we're actually going to go through the machinery that makes all that happen. So we want this kind of a thing. We want a set of bounding boxes, and we want a set of...
Hey brother, just noticed that you solved the backtracking problem in your first try. Amazing, keep going. Thanks, man. I mean, that one was, today's one was pretty simple, I reckon. But, like the other backtracking problem, the palindrome partitioning one, I did that yesterday. That was there was bugs there that I solved finally, but it took me forever. Like I was getting pissed a little bit. But yeah, today was better. Way better. Like it seemed pretty straightforward, today's solution.
Probabilities for each class. We'll deal with which pixels are which later. So this is the system in action detecting people in cars. You can imagine why this might be an important task. So what are we going to look at? We are going to discuss object detection in general, and then look at this sequence of region convolution task later. On object detection. So we're actually going to go through the machinery that makes all that happen. So we want this kind of a thing. We want a set of bounding boxes, and we want a set of probabilities for each class. We'll deal with which pixels are which later. So this is the system in action detecting people in cars. You can imagine why this might be an important task. So what are we going to look at? We are going to discuss object detection in general, and then look at this sequence of region convolutional neural networks. RCNN, fast RCNN, faster RCNN. And there is something valuable about that sequence, going through the sequence, even though, of course, you'd just start with faster RCNN today. But you can understand the sort of the sequence of ideas as they develop, and maybe that will help you as you try to design your way through a sequence of ideas to solve some task. So we'll be talking about sliding window classification, and then talk about how do we actually do it within a region-based convolutional neural network, and explain design issues and trade-offs involved. So this is what you should be able to do. Okay, so classification is object detection is locate them in the image. Classification says, is this well, what is this? Is this a cat, dog, couch, whatever? Detection is, where are the faces? Face detection, for example. So detection, we often do by doing classification lots of times over. So I take a window and say, is there a face here?
Should get some water, be right back. I gotta not hunch my head too much. Gotta keep my head straight because, you know, reduces the stress on the shoulders. Know what I mean? I gotta reduce the stress on my shoulders. carrying the weight of whatever's burden, whoever's burden, my own burden. You know what I mean? Gotta move these arms. Imagine me at old age doing this every day. I think I need to like... One thing for sure is if I had like two computers, I mean 2 screens like this, maybe I wouldn't need to hunch down and look on my second screen, you know? That's like an ergonomic issue. Okay, I think that's fine.
I move my window across a bit and say, is there a face here? So the photo app in your phone actually does something a bit like that. Of course, it uses clever tricks to minimize the compute requirement, but it's basically looking for faces in boxes of different sizes and many different locations across the phone. You find the faces, it can auto-focus on the faces, or it can wait for a smile, or it can wait for people to be not blinking. It does all of those kinds of tricks that we do in a modern phone app. Okay, so what we're going to do is have a bunch of patches, windows, and say, is this the class we're looking for, or what class is this? Usually what we do is we have an n+1 classifier. So we can say, is it one of the things I care about? Let's say I care about people, cats, and dogs. Then I would have a 4-label class classifier that says it's a person, it's a cat, it's a dog, or it's nothing. Most things are nothing. And then I'll label each window by what it is. So I can take this window and okay, so what we're going to do is have a bunch of patches, windows, and say, is this the class we're looking for, or what class is this? Usually what we do is we have an n+1 classifier. So we can say, is it one of the things I care about? Let's say I care about people, cats, and dogs. Then I would have a 4-label class classifier that says it's a person, it's a cat, it's a dog, or it's nothing. Most things are nothing. And then I'll label each window by what it is. So I can take this window and I can say, This is not going to be a person, cat, dog task. Is this a chair? No. Slide it across, keep saying no, and I've got a whole bunch of windows to say, is this, or is there a chair? You can imagine I do a lot of computation here. But now, the chair might be closer, so I have to check bigger windows as well. So you can imagine that this is going to become very slow. And then some things I'm looking for aren't square, so maybe I have to check some rectangles too. So this is prone to a combinatorial explosion over the positions of the window, the size of the window, the aspect ratio of the window, and so I have to worry about all these things. This makes for a lot of windows, and so we have to use a very large number to find the things we're looking for. We might detect a whole bunch of things with those windows, and then we've got to decide, well, hang on, you know, we're looking for lamps and chairs or cushions, or I don't know what that one is looking for, maybe it's looking for the table. I have to decide at what point do I think there's something there, because I've got these, in that example, person, cat, dog, I had 4 classes. So how much does it have to be person before I say, yes, I think there's a person there? So there's another free parameter, which is what is the threshold for detection? And if we have a window that's above that threshold, we say, yes, that's a hit. So it makes evaluation tricky. We can say, is this a good result? Well, it depends on, you know, what you thought you were looking for. If you were looking for lights, then you found the lampshade on the left, but you didn't get the whole lamp, and you found the lampshade on the right, but you got much more than the whole lamp. And then the other thing here, that wasn't a lamp at all. Even though I suppose within the window, if you kind of squint and blur your eyes, it might look a bit like a lamp. So we need a way of evaluating, what we've got is ground truth. So I can go in with a tool and draw some rectangles and say, these are where the lamps are. And then what we need is a way of training our system to find the right answers. So the principal method of scoring, well, I found this rectangle and you had that rectangle of the same class. The traditional way, the way we typically score that is to use an IOU measure, intersection over union. So the intersection is, so the ground truth was the green rectangle, the network thought the pink rectangle, or the system thought the pink rectangle. How do we score it? We look at the pixels, count the pixels inside both rectangles, and divide by the pixels that are inside either rectangle, which looks like this. So if I have 2 rectangles, I can find their intersection at the top, that's one area. I can take their union at the bottom, that's another area. So this is a score of something like 0.3 as an intersection over union, it looks to me. So we got, our intersection over union is 30%. We need to have the union, we can't just say what fraction of the green rectangle pixels did we find, because we need to have that union, because otherwise what we learn is make the rectangle huge. And it would guaranteed to find the pink ones, the green ones, wherever they are. Make the pink one huge. So if you union them, you pay a penalty if you find false positives as well as for false negatives. So if you think about it this way, these are false negatives, these are false positives, and so you pay that penalty. So let's say these are our rectangles, the intersection over union, the intersection is 3 by 6, which is 18. The union is, let's do this, that's 6 by 8 is 48, plus 3 is 51. So I have 18 over 51, which is an IOU of 0.35. Okay, so that's how we assess, and it's actually going to be the score that we use to put a loss when we train our neural networks. All right, which is an IOU of 0.35. Eight is 48, plus 3 is 51. So I have 18 over 51, which is an IOU of 0.35. Okay, so that's how we assess, and it's actually going to be the score that we use to put a loss when we train our neural networks. All right. We are going to, and this will carry on over to our neural networks, we're going to treat detection as classification in lots of windows. So the question in the neural networks is, where do the window proposals come from? And that's going to be the key. If we have some threshold that says, yep, we think we found the object, then we can return these as our positive results, and then we can train our network or train our system to improve on its results. What goes wrong? If we detect a very large number of possible windows, then of course it's very slow because we've got a lot of things to process. Or there are, naively, a very large number, which is going to make our system slow. It creates massively large chances for detection of too many things because most of the things should be 0, but there are lots of opportunities to accidentally say there's something, so we're going to get lots of false positives. And if we have lots of things that share the same space, we need to disambiguate what's going on in the space. So we need to deal with the fact that there might be a person holding a cat, and we've detected the cat and we've detected the person, and we need to figure out how to evaluate that and how to score it. So, 5-minute intro to RCNN. This was the problem with the sliding window approach, right? There are some number of scales. Some number of shapes, the shapes being the different aspect ratios, and some number of locations. And we want to, first of all, think about how to speed that up in parallel to we've detected the person and we need to figure out how to evaluate that and how to score it. So, 5-minute intro to RCNN. This was the problem with the sliding window approach, right? There are some number of scales, some number of shapes, the shapes being the different aspect ratios, and some number of locations. And we want to, first of all, think about how to speed that up in parallel. So what we're going to do is treat it effectively as a convolutional problem. So now the convolutional problem is not classifying each pixel, it's classifying a large number of bounding boxes in the image. But if you do this, it's still going to be slow and there's still a lot of false alarms. So what we're going to do is an intelligent two-stage approach. So the first stage is going to say, I think there's a something here without knowing what it is. So that's the first stage, is going to generate the bounding boxes that are promising without doing the whole classification task. The second stage is going to tell us what's inside each box. So the first stage, they're not the color code, no color coding, because what we've done is generated bounding boxes that look like they contain things. So how are we going to do this within a neural network architecture? Well, actually, RCNN, the first stage is only a bit neural netty. Actually, it uses classical methods to get itself started. So we want to identify a small number of regions. These are going to be the proposals or regions of interest, and then we're going to figure out what's happening in them. RCNN uses selective search to do this. So what does that do? It is a superpixel algorithm. So we're going to segment our image into superpixels, and then we're going to use a classical method to recombine superpixels together, just as we did back in that very first segmentation lecture. And based on color, texture, size, compactness. So there's texture in here. It's not just color clustering. It's looking at the textural structure of the colors within the region. And then that's going to generate some small number as we iteratively combine. We're going to get some small number of blobs, and then we're going to take bounding boxes for each blob, and that's going to be the input to stage 2. So this stage is purely classical in RCNN. So there's our input image. We find our regions of interest from that selective search. That's going to be typically a reasonably large number, like 2,000. But nothing giant like the hundreds of thousands that it would be if we densely searched. We are going to abuse geometry and transform all of those things into square images. We're going to resample at 224 by 224, pump them all through a classifier convnet. So 224 by 224 is what all of the early AlexNet, VGG, all of those networks use that size to classify things. We use one of those networks, a convnet, and that then gives us a class for each region, including the there's nothing here class. It also says, oh, that bounding box you gave me, that was too big or too small. And so what it does is it says, actually, it might put the origin at the center, and the left-hand edge of the bounding box is -1. It says multiply that by 1.05, it needed to be bigger, or multiply it by 0.8, it needed to be smaller. So it gives us, or add on -0.2, add on plus 0.05. It will move that boundary relative to where it is. And it'll do the same with the right-hand boundary, the top boundary, and the bottom boundary. So we have a separate head on each convnet that transforms the bounding box to be correct. And this is based on looking at the pixels in the image. So you have some proposal here, and you end up with some corrected bounding box. This is a kind of an extreme example after this bounding box regression transformation. Okay. So we have the original reason proposal. This is we're parameterizing this as the center, x, y, the height and the width. We have transformations to the center, height and width, and the goal is to compute a new bounding box. And so we say, well, the new bounding box was the original x plus the transformed x times the original width of the bounding box. So it moves it in proportion to the size of it. Ditto for the y, and then we scale these values, t height, t width, and the transform are the logs of the scale change that we're making to the bounding box. So that enables us to correct the bounding box to correctly reflect. I said a 5-minute intro, we're a minute over, so I will stop there and pick this up next time on Friday. Thank you.
This material is made available to you by or on behalf of the copyright website.
I guess we're at the pointy end of semester. Okay, so it's my pass will get going. I guess we're at the pointy end of semester, and there are lots of deadlines for you folks, so appreciate your attendance. We are talking about RCNN, the Region Convolutional Neural Network, and just quick recap. So that uses merged superpixels to obtain its region proposals, then samples those regions in the images, resamples as square images that it passes to a neural network. So there is a convolutional neural network that takes those regions. It's pre-trained on ImageNet, but we replace the last layer, which in ImageNet classifiers, whether it's AlexNet or VGG or ResNet, have 1,000 classes, which are the ImageNet classes. We remove that and we put in a last layer that is n+1 classes for the classes we care about. And the reason, if we recall, for the +1 is we need to be able to say this bounding box has got nothing in it. So this one has a cat, this one has a person, this is a dog, this one has nothing, is the n+1 class. If you like background, this is not part of not a foreground object, it's just part of the scene. So the ConvNet, we train on n-way detection, and we have positive objects, and we use an intersection over union threshold of 0.5. So remember, our region proposals are coming from these merged superpixels. We have ground truth bounding boxes, and so we say if the superpixel generates a region which has an intersection over union of more than 0.5, we treat that as a positive, and so we train our classifier to say it should be this class. And then we also sample background regions that have very low intersection over union, and we train our classifier to say those are background. And we bias our input so that 75% of the training set says background. In practice, when we deploy it, we're going to end up with more than that. So the features from the CNN, so before the last layer, are used as input to two things, remember. So we've got the label classification, the n+1, and a bounding box model, which does a regression on the bounding box from the merged superpixels in order to give us the region we want. So this is the picture. We have those regions from merged superpixels. We resample them as square images. They go into a conventional ConvNet that tells us both the class and the bounding box for regression. When we test it at inference time or for assessment time on our withheld validation set, we put in a test image, we compute region proposals using selective search, which is the merged superpixel method. Each region gets put through the ConvNet, and the detections we declare are those regions with high class confidence scores. So we have to have some threshold on the confidence score for the foreground objects versus the background class. So we need to exceed some probability before we say our network has detected something. That can be based on a threshold, or we can select top K, and that can be overall or per category. So there are decisions to make in that. So this is what CNN generates. Person, bird, great, dog or swine, i.e. a pig, antelope, interesting, or mushroom, bell peppers. So you can see that it gets a lot of things right, but it also gets a lot of things wrong. and there are some interesting overlapping bounding boxes. So these are just random samples from the network, so you get some sense of its performance. The author of the paper also chose some other images to illustrate the kinds of things that go wrong. So the chair, that's fine, but actually that TV or monitor, that's just a reflection of a window in a window, not a TV or monitor. That's a snake, or maybe the two together are a bird. You'll see in a sec why maybe that happens. Is this a tennis ball or a lemon? So you can imagine the kinds of mistakes that the network makes. The bird example, hang on, why is that not working? There it is if you imagine sort of blurring it out, the snake plus its reflection looks a little bit like a bird, maybe. Okay, I'll skip over this, but note in particular the advantages over sliding window are that we've selected just a few windows to classify, which gives us a huge speed up. Disadvantage is that we're still classifying a lot of windows, and the region proposal step could miss some objects. And we're also processing each window independently. So if the windows overlap, we are resampling our image with the same pixels twice and putting them into different instances of ResNet or AlexNet or VGG, which takes us to fast RCNN, because that deals with that recomputing the same stuff over and over. So the major change is that instead of using, we still keep the same region proposal system, but instead of resampling the original image to classify each region, what we do is we have a backbone that computes a bunch of features first at each pixel, so that's a large chunk of network. Then we resample that output for each window, typically at a reasonably low resolution. So we have some deep convnet, we have a region projection, we resample the output of the convnet, and then that goes through some small fully connected layers and gives us a softmax over the classes and a bounding box regressor. And the idea is that this bit of network is much smaller than this bit of network. So the region proposals come from the last conv layer of the backbone. So we run the whole image through the convnet. That gives us a last layer feature map. We project our region proposals on, and just these come from selective search, just as they did in RCNN. We crop and resize these features, and how do we do that? So we've got our bounding box. Of course, that doesn't line up because we've downsampled in our backbone network, so it's at lower resolution than the input image. We take our bounding box, we need to snap to the closest, and then resample that, for example, into 2 by 2 by averaging these 4. So it's a very crude kind of nearest neighbor snap to type resampling approach. That makes it very fast. Dividing into a 2 by 2 grid, and we max pool within each cell to get the input. So we're not averaging, we are max pooling within each of those cells to get the input. That gets us 2 by 2 by 512 features, which was the depth of this thing, the number of channels in this thing. And then that goes into the classifier, the per region classifier and bounding box regressor. And the idea is, this is a small thing, this is a big thing. We are sharing the big computation amongst all of the region proposals. So if we've got 2,000 region proposals, we're doing 2,000 of these, but only one of these. And so this is much faster. What architectural backbone do we use? So we can this backbone typically is most of something like AlexNet. This might actually just be the remainder of the AlexNet, if you like, or some simple network. So the backbone there can be AlexNet all the way up to the point where we're about to flatten, and that gives us this output that we're resampling, or we can use ResNet up to the point where we flatten. So we're using all of the convolutional part of those big networks to provide the output at this layer, and then this thing is a tiny classifier, just with with the flatten and a couple of fully connected layers, but the input was only 2 by 2 by 512, which is 2048 activations after we flatten. Okay, we train on regions sampled from images much as we do in RCNN. We sample a small number of images and a large number of regions, which enables us to take advantage of that efficiency because we're sharing the backbone. Again, we sample so that 75% is background, and we have a multitask loss again. So this is the bounding box loss, this is the classifier loss, and the bounding box it's kind of trying to make us do well on intersection over union, but we look at the absolute error between if you like, the width of the bounding box and what we predict, or for each edge we look at where it is versus where we predict, look at the absolute error relative to the size of the bounding box, and we have some loss that doesn't penalize small things too heavily, but it doesn't grow quadratically, so it's a kind of a robust loss. So these kinds of objective functions are designed so that huge outliers don't bend the whole thing out of shape. They don't have a quadratic influence on the loss function. This is an example of a thing that we're not doing in this subject, but there's a whole branch of optimization, which is robust optimization, which replaces objective functions like sum of squared errors with other objective functions that are much more permissive of large errors, but still behave as you wish them to behave for small errors. So this is an example of that applied into this field. And we don't do this, of course, for background windows, because the background windows don't have a true width and height. They are just whatever the background windows are. Okay, so big speed up, particularly at inference time. The key problem here is that we are still using selective search for the region of interest, which comes from the superpixels, the merged superpixels. If that step fails to detect the object, there's nothing we can do with our clever neural net to pick them up again. And because it's a somewhat brute force approach, there are going to be lots of objects that we miss. Which brings us finally to faster RCNN to deal with that last weakness. So fast RCNN has the shared backbone. We're going to see that again. But faster RCNN ditches selective search with superpixels and uses the backbone to propose the regions itself, which makes it trainable via backprop, whereas selective search is not trainable via backprop. It's closed form and fixed. Okay, so here we are. We have our, let's say it's ResNet. By this point, we're using ResNet for everything. Here's our ConvNet, which is ResNet, and we get some feature map. Now, that feature map, remember, is at lower resolution than the image because the ResNet contains convolutional downsampling stages. So we've got a low-res representation of our image here. And then we use that to do two things. The first thing we do is we use it to replace selective search by having each pixel in the low-res map propose actually more than one bounding box. So there are I think 3 proposals per pixel. We call those anchor points. In the feature map, that generates a bunch of region proposals. We then do the same thing we did in fast RCNN of resampling the output here according to those proposals. At the same time as we propose a bounding box, we're asking the proposal network to guess what class it is. But we don't use that class in the long run. We resample and then we have another classification loss. So we're estimating bounding boxes and classes once, and then we're doing it a second time. Well, this has got the reason, obviously, we've got a bounding box regression loss here because these are the proposals that go into stage 2. Why is there a classification loss? So it's a general truth that the more knowledge you bring to bear on a system, the more training signal you use, the better that system becomes. So this classification loss is a very direct feedback into this classifier, into this ConvNet representation generator to capture information about classes. This gets used for nothing in the end. This gets used to generate the initial proposals that get resampled that we then refine. So this regression loss is a refinement on this bounding box, and this classification loss is the one we end up thresholding on and reporting on. The region proposal network, we get these convolutional features. Each of these pixels in the low resolution image is an anchor point. So here is one of those. That corresponds to this region here. And it generates K. My recollection is K is 3, but it might not be. It might be 5 if I've misremembered. But it generates some numbers of regions with a fixed size and aspect ratio. So it might generate 4 in this case like this. So it says, okay, here's a small one, here's a large one, here are 2 with different aspect ratios. And for each of these 4, we predict where the window is centered and what the object class is. So that gets our feature maps, and then that gives us our region proposals from here. And then for each of those regions, we do exactly the same as we did with fast RCNN. So we have all the expected losses. The classification losses are cross-entropy loss, including background class. The regression loss is that smooth L1, which was that robust loss between the true and predicted bounding box parameters. We sample R regions from N images. In this instance, we sampled 256 regions from 1 image per mini batch. And we sample not 75% background now, only 50% background. Basically, you see papers where all of these numbers just sort of come out of the woodwork. And what's happened in the background is the authors have found, oh, it's not performing very well, I'll tweak that number. Deep learning as a field is kind of full of intuitions that you gain from experiment over time. And so as you become practitioners, assuming that something that's interesting to you in this area, you'll acquire all these kinds of insights and instincts as to what the right numbers should be. And then the paper tells you we use 50%. It doesn't tell you we tried 75 and 60 and 40 and 25 and 90 and all sorts of other things as well. But a lot of these numbers that they happen to pick are rather carefully chosen, and if you change them wildly, you find that your performance drops a lot. Okay, so we've got the region proposal network plus the fast fast RCNN reclassifier, and we have to train both sets of outputs. For this paper, they do something that you don't often see, which is this alternating between training the region proposal network. You might start there, right? I mean, there's no point trying to classify badly selected regions. At the beginning, the region proposals are going to be terrible because the network hasn't learned anything. And so there's no point in training stage 2, really, at the beginning. So you train the region proposal network, then you train the piece that sits on top, and people do this because it takes less memory. You can pre-compute the region proposals and the representation, and then use that to just train the second part of the network. So a lot of these kinds of decisions, like alternating training, are taken based on the constraints of the compute hardware. So it is even faster, so it's much, much faster than the original RCNN for inference at test time or at operational time. And because it's got this kind of modular structure, it means you can make changes and transfer learn between different tasks quite effectively. There is a speed and accuracy trade-off. You make the network deeper, it becomes more accurate, but it becomes slower. Okay. I guess you can, as I say, you can read this as well as I can. So what have we done? We're detecting objects by classifying different regions. The regions are either, in the case of sliding window, exhaustively selected, or they're proposed by some mechanism. And that mechanism can either be a classical computer vision mechanism, or it can be a deep learning mechanism. And we'll come to YOLO, which is kind of just doing the first stage. It just uses the first stage. You only look once. You don't do a resampling, which is why it's called YOLO. You only look once, not live. We'll have that in the next slide deck. How do we select the region proposals? Well, we looked at that, and then the class imbalance background is by far the most common class, right? We might have 10 or 20 objects in a scene, but we're generating 2,000 windows, which means that actually 99% of the objects are background, but you don't train at 99% because that massive imbalance makes the classifier say everything's background, and it never really learns the things you want it to learn. But you still, because so many are background, you bias it a bit. So you rebias your distribution, and that turns out to be helpful. Okay, let us go to this slide deck. Okay.
I'm just going to the toilet, be right back.
we're going to start this slide deck with a few psychophysics experiments. So are we in the mood? All you have to do is raise your hand when you've spotted the figure. Okay, so the task is to find this object in the scene. So go. Excellent. Yes, super quick, right? Ready, steady, go. Super quick, easy, right? Okay, next one. Ready, steady, go. Right. So this is a classic psychophysics experiment. It's suddenly much harder. Why is it much harder? Here's another one. Ready, steady, go. Okay. So this is an interesting problem. So the first ones are the phenomenon called pop-out. So this one, the features of the circle are radically different from those of the fives, the twos and fives. And the person, of course, is radically different from the other person and all the rest of the scene. But the fives and twos are much more similar, and the, I guess, what are they, safety markers, fiducial markers are very similar to each other too. There's a theory of human vision called visual integration theory by a woman called Anne Treisman, if I remember correctly. And essentially these things, the ones that pop out because there's a feature you can look for that is absent from the other class, from the distractor. But the kinds of human primitive features for the 2 and the 5, you have to find a conjunction of different features. So another version of this is you have to find you have, I don't know, squares and circles. So you have, and you want to find, let me get this right. So you have you have black objects and red objects, squares and circles, and you want to find the red circle in amongst a field of red squares and black circles. And because of the conjunction of red and circle, you have to search through the space. Similarly, you have to search through the space here, and you have to search through the space here. So it turns out these tasks for humans take time that is linear in the size of the distractor space. So it becomes a search problem. Okay, so we're going to have a quick look at single-stage object detectors, i.e. YOLO. We'll talk a bit about instance segmentation. So we've had bounding boxes so far. We'll talk a bit about mask RCNN, which gives us pixels. And then we will talk about how we evaluate object detectors and moving beyond patches. So this is what you should be able to do. One of the algorithms we're going to talk about is the non-maximal suppression, and we'll talk about mean average precision as assessments, and then you should be able to compare various things. So YOLO, instead of faster RCNN, we just predict a heat map for each class directly within the CNN. This is this the bicycle heat map or the dog heat map? Oh, there's a dog heat map, which is in blue. The yellow is the bicycle heat map, and so on. And we end up with these detections. So what does YOLO do? We have a set of n class probability maps, but m bounding box parameter maps. So we have a loss for the maps because we can label each pixel between the true and the predicted maps with some weighting. The bounding box parameters, which is the other output, have a a more significant contribution to the loss to make them not be forgotten. And then there are cells that don't contribute to the classification loss. So just as in faster RCNN, we are emitting anchor points, bounding boxes, and class labels. And if a grid cell generates bounding boxes that don't correspond to real objects, then they don't then you don't pay a classification loss there. So we penalize bounding box parameters based on the confidence score for the object from the classification head. And we're producing M bounding box parameter maps per pixel in our output. So these are per anchor point, if you like, in our output. What we end up doing is we end up encouraging different ones to specialize for different kinds of objects. So this is this is typical output. We have 3 horses. How do we only get 3 horses? YOLO, this is YOLO V1. I think there's now a YOLO V5 that's very popular. For a long time, I thought it was the same research group producing new versions, but it turns out, of course, it's open sourced, and so it's kind of forking the code, and they don't really have a sort of a single common thread, but there are lots of different versions out there. There might even be a V9 out somewhere. But typically, if you want to solve these problems, YOLO is where you would go first today, because the performance is better than anything else. And it has the advantage, because it doesn't have the 2-stage process, that it's much faster than even faster RCNN. Yeah, I mentioned there are lots of versions. But because we're not doing the refinement step on the bounding boxes we get from YOLO have less accuracy, because it doesn't have that let's make it better stage, because there's no second stage. Okay. So you predict the class and a set of bounding box heat maps. We deal with the fact that there are different sizes of objects in the scene by generating region proposals or bounding boxes at lots of different stages as we're downsampling. So at each stage, we do it relative to that size of image in the downsampling process. So we have detections and bounding boxes coming from different resolutions in our backbone. And so as we're sampling going down in size, what we're doing is effectively generating larger bounding boxes for the whole scene. So we can have large objects and small objects. So we're not just doing it from a single resolution, we're doing it at kind of multiple resolutions as we go. And then we get a big bag of proposals from the sizes. So this is the single, this is single shot multi-box detector that does this. Okay, again, we have lots of bounding boxes and class confidences and 4 bounding box parameters per proposal. So the anchor points are in multiple convolution layers, which is this connection I was referring to here, and it lets us detect objects at different scales. This is what SSD ends up looking like, generates large bounding boxes and small bounding boxes much more happily, and gives us good proposals. A lot of these ideas are in more recent versions of YOLO too. So it's faster than the two-stage methods, region proposal with follow-up, but it's generally less accurate because, again, there's no refinement stage. Anchor points in early layers, yes, they help with prediction of small objects, but if you think about it, these early layers have also had less processing. So there's less semantic knowledge about what's going on in these early layers, and they haven't had the advantage of context of, you know, whole of scene context, which means that they are going to be less accurate in terms of classification too. What can we do instead of bounding boxes? So CornerNet, rather than predicting a center and a width and a height, has a prediction of the top left and bottom right, which is just a reparameterization of the bounding box. CenterNet just predicts the central point. One thing one of my students did was, first of all, to do per pixel classification, and then every pixel says, I think here is where the center of my bounding box is. And then you cluster those estimates. You then know everybody that thinks this is the same, it's the same class and the same pixel, so we can then put a bounding box on that. There are lots of ways of solving this particular problem. Okay, so single stage detectors like SSD or YOLO basically stop at the first stage that generates first stage region proposals and classifications directly. And you can think of them as being like part one of faster RCNN, if you like, except that, of course, we can do obtain bounding boxes at different scales in SSD in different ways. Okay, so moving on to pixels. So we labeled pixels before. Now we have bounding boxes. What we'd really like is something like this. So how do we separate out the instances and get actual pixels? We have here two bounding boxes from YOLO or faster RCNN. So we run the object detector, we get the bounding boxes and the labels, and then we have another process, if you like, that gives us the segmentation. So we have this bounding box, and we know it's a cow, and so we then want to obtain the pixels that belong to the cow. So this brings us to the final version of the RCNN series called mask RCNN. This was faster RCNN, you may recall, so two-stage, generate bounding boxes, first attempt here, resample, compute again the class, and refine the bounding box. So what we're going to do is we're going to add an extra section on. So this is our class and bounding box here, but we're going to take that output and run some conv layers, and what that's going to do is it's going to predict a binary segmentation mask, and actually there is an output one per class for this. So the patch loss, we've got a third loss now. We've got the class loss from here, we've got the bounding box loss from here, and then we have a mask loss that tells us which pixels. So then now we've colored the pixels within the bounding boxes belonging to the object. So because we generate a mask per class, we only apply a loss to the correct class. So in this case, we have a person, but we might have cats and dogs and bicycles. We'll generate separate segmentation on the assumption that it's a cat, dog, or bicycle as well as a person. Because it's really a person, we only feed a loss back into the binary mask for person. This binary mask, of course, it ends up being probabilistic because the output goes through a sigmoid to clamp it between 0 and 1. Large values say, I think this is very probably part of the person. Small values say, I think this is very probably not part of this person. And mask RCNN generates beautiful looking results like these. We had a look at some of these before. And indeed, you can run it on video sequences, and so now we have labeled pixels, we have the bounding box and the pixels for each of our objects, and probabilities, and this is kind of where we wanted to get to at the beginning of this sequence. Another video, similar data set showing the same thing. Okay, so, sorry, too far. Things like mask RCNN give us pixels as well. So we can do instance segmentation, and which gives us the bounding boxes followed by a binary segmentation within each region. Mask RCNN is the main tool that people use to do this. But people generate new tools like my student that did the where is my centroid type trick. It fails when you have like a small car directly in front of a large car because the centroid for both is about the same. We didn't ever solve that instance separation problem. Okay, so how do we evaluate how we've done? So the detector will generate a large number of bounding boxes that have high scores. So in this instance, the detector has generated 4 separate bounding boxes, all of which have an estimate that what we're looking at is a mug with a confidence score of over, let's say, 0.5. So it believes that with high probability of at least a half, and remember there are probably lots of classes, that each of these bounding boxes contains a mug. And so what are we going to do to deal with this? So if it's the same, you know, it might be 4 separate mugs, or it might be that are near each other, or it might be that there's actually only one mug. So do we treat it as multiple detections, or do we just select one of these for our final prediction? So in order to do this, we need to have some mechanism really for merging together multiple estimates. So where we have large numbers of bounding boxes, what we're going to do is start with the highest scoring, the highest confidence bounding box, which I think is that 0.92. I can't see the one that's occluded there. And then we are going to remove other bounding boxes that have a high IOU with our bounding box, that also think it's the same class. So for mugs, we're going to find what's the highest mug bounding box in our image, and then remove all the bounding boxes that have a high IOU and inevitably therefore have a lower confidence score. Let's say the threshold is something like 0.7, which means it's really very close. In this instance, these 3 would all have a score of 0.7. This one actually probably wouldn't. It would be below 0.7 as an IOU. Then you take the next, you've thrown a whole bunch of things away, you take the next highest scoring bounding box. So this is a way of trimming down your set of bounding boxes that you use. And we do that separately for each class, because we don't want to merge a kettle and a mug, because there might well be a mug in front of a kettle or something like that. Because they're different classes, we don't want to merge them together, so we take high confidence score for mugs, we run through that hierarchy. We take high confidence score for kettles and run through that hierarchy. So here we have 4 bounding boxes, 4 dog bounding boxes in the image. And at this point, the computer doesn't know whether there is 1, 2, 3, or 4 dogs in the image. So we have 4 different scores for dog. So we find the highest, that's 0.9. So there is our bounding box for 0.9. We look at the other 3, and we compute the intersection over union between the blue one and this red one. That's, and the orange one here, which is 0.78. We do with the purple one, that's 0.05, and with the red one, that's 0.07. So of these, only the orange one is above 0.7. So we remove the orange one. We now take the next highest score, which is 0.75, the purple one. The intersection over union with the red one is 0.74, so we remove that, and we're done. We end up with 2 dogs in our image. So we are discarding weaker dog detections that have high IOU with stronger dog detections, if that makes sense. Unfortunately, when you have a very cluttered scene with lots of overlap, you can be, this can cause you to remove things that have been correctly detected as separate objects. And then you have to make a decision, how much does that matter versus counting the same thing multiple times? Usually you don't mind missing a few, or if you do mind missing a few, you have to refine your system so that it's more capable of detecting different things. Okay, so now we have to evaluate it. So this is a refinement stage on the output. We've trained our faster RCNN.
Hold on. How is this even real? How is there one car right here about to crash into all of these motorcycles? What the heck is this on the back of a ute? Everything else looks fine, but damn, now one person out in this almost made me believe it was ChatGPT or something.
Or our YOLO, now we want to evaluate how good it is. So we have a test set, we can run detections and do non-maximal suppression to remove overlaps. Now what we want is we're going to compute an average precision per object category, and we're going to construct a precision recall curve to do this. So have you come across precision recall curves? Is that a thing that means something to you? Okay, quick aside. A precision recall curve, let's say you have some medical test and it's going to detect a condition or not, but we can apply some threshold. So I'm going to do, I don't know, some biopsy, and I'm going to do cell counting of a particular kind. I'm going to stain the cells, I'm going to count how many cells there are and how many cells have a particular condition. Maybe it's a cancer marker or something like that. And then I'm going to say, okay, if there are more than 5% of the cells have the marker, I'm going to say yes. Now that 5%, that's a free parameter. I can change that. And I could make it, well, I could say actually maybe it's more than 10%. What's going to happen if I go to 10% is I'm going to return fewer positives. But those positives are more likely to have the underlying condition, right? Because I've raised the threshold, the bar, to detect them. So the precision is of the things I say, yes, I think this person has cancer, to how many of them actually have cancer. What fraction actually have cancer? That's precision. Recall is, of the people who actually have cancer, how many of them have I detected? So that's precision and recall, right? So what I can do is I can steadily change that parameter, and what will happen is if I start with a large number, that'll have very high precision but low recall. As I reduce my threshold, the recall will go up and the precision will come down. So we're going to do a similar thing for our objects. So first of all, we sort the dog detections that we have retained from the highest score to the lowest score. So this is after non-maximal suppression. And so I've ended up with 5 dog detections in my image. And then I have 3 ground truth boxes for real dogs in the image. So what I'm going to do is I am going to run through all the detections by score and look for a match where the IOU is more than 0.5, or find the highest ground truth bounding box that has an IOU of at least 0.5. So if I find one, what I'm going to do is mark that as a match, and I'm going to remove that ground truth. So, okay, so I've detected that real dog. Otherwise, we mark it as a negative. So what happens is we've matched, the first one matched, we have 100% precision because everything, if I put my threshold here, everything above the threshold matches something, but I've only found one of the 3 dogs. So that's a precision of 100% and recall of 1/3. I now go to the next one, that matches this one, that's great. So the precision is still 100% and now the recall is 2/3. I go to the next one, that does not match the remaining dog with an IOU of greater than 0.5. So now my precision is 2/3 and my recall is still 2/3. So out of the 3 above this threshold, only 2 match things, and I only found 2 of the 3 real dogs in the scene. The next one, unfortunately, also fails to match, so now my precision drops to 1/2, 2 out of 4. My recall is still 2/3. There is my precision of 1/2, recall of 2/3. The final one, I'm lucky it matches, so that gives me finally 100% recall, and my precision is now 3/5, 60%. So this is my graph. The average precision is the area under that curve. So if I did really well and I detect 1, 2, 3, the correct dogs, and then the other ones don't detect, then I'd have 100% because it would run 1/3 recall, 2/3 recall, 3/3 recall, and then at 3/3 recall we'd drop to 3/4 precision, and then 3/5 precision, but that wouldn't matter because we'd be running down this axis here and we'd have 100% average precision. In this instance, we lost a chunk of the box because we had 2 false hits before we got the last correct hit, and we're missing a bit. Sometimes we never get all 3, and so we're missing a whole chunk on the right-hand side of the recall graph. So what is the best possible average precision? I've just described how it can be 100%. And that's when we have the first 3 match the first 3. But in general, you get some other shape. Okay, so the average precision is the area under the precision recall curve. Then our metric that we use to evaluate our detector is a thing called mean average precision, which is, I compute that average precision area once per class, and then the mean is that quantity averaged over all the object classes. And again, of course, we average over the whole, we do this per image, per class, and then we average over the training set, over the test set, in order to get the per class average, and then we can average those together to get the mean we might get a bird average precision of 0.65, a cat average precision of 0.8, dog of 0.86. The average of these is 0.77. These get added together unweighted, even if the classes are imbalanced in the data set. Then there's a more sophisticated version of mean average precision, because there was still a free parameter in the algorithm, which was this IOU of IOU of 0.05 here. So the COCO mean average precision repeats the whole exercise with sampled IOU thresholds starting at 0.5 and working up to 0.95 in 0.05 increments. And then you average over all those. And it's designed to be a more flexible measurement tool. We might have a mean average precision at 0.5, it's 0.77. As we raise our IOU threshold, it's going to drop, and then we can average all these numbers and get a COCO mean average precision averaged over the various choices of IOU threshold. All right, I think we will just summarize that and highlight the point that a single number is not very informative because we're trying to solve lots of different things. So how accurately is it detecting the different classes? How accurate are the bounding boxes? What kind of errors is the model making? Is it making lots of false detections, low precision, or is it missing real detections, low recall? Is it misclassifying things and so on? So we tend to want to have a number of scores to assess the performance of our system. We'll finish this and talk about diffusion models next time. Diffusion models are not examinable. The remaining slides from this deck are examinable, so I shall see you next week, Wednesday, for that. And then on Friday next week, we'll do a revision lecture that is a high-speed forward pass through the course and opportunity for you to ask me questions to explain things in more detail. So I'll see you next week.
Alright, I'm going to eat some lunch, go to the gym, be back. I'll put on some music. I'm gonna go gym now. Alright, peace. Alright, I'm back. So, lunch, gym, shower, scheduler development, and tutorial. Now there's not going to be any more CV tutes, so I can delete them from now on. I can delete these from now on as well. Looking alright, I guess. Could be clearer, to be honest. If I... Give me a sec. I gotta do it on this phone. So you guys can kind of see just randomness at the moment. So bear with me while I check something, which is to get rid of the calendar sync integration from an app, or at least change it to a different event calendar. Maybe iCloud versus events. I'm tempted to just create a new calendar. So I'll just do that real quick. So there was an events calendar. This is for my okay, it has to be this. So I gotta create a new calendar. You couldn't create the calendar. Why do I have an iPhone calendar? Is this where I'm meant to put my iPhone stuff, I guess? Alright, fine. Let's change it to iPhone calendar. Which means we have those calendars changed. Sure. It should get reflected. In this calendar at some point soon. So it doesn't matter now. I can revert things to the way they were. Okay. turn on the computer. Thing is though, do I want to use Windows at the moment? Or am I fine without it? Depends on what issues I have. Alright, so if we have go to my GitHub. Yeah, you know what, I am just going to not use anything else but my Mac for this. That means, though, that I'll just have to turn this off once I'm in. It'll mean here that I want to access scheduler. I mean I need to do some thinking. Also restart to update, which I'll do right away. And we have this, which I'm going to shut down. Cool. Oh, it's actually unfortunate. We have 100 CPU usage at the moment. Why is it that bad? Perhaps it's just meant to be, and I'm meant to use something else. What's causing this? Alright, well, we'll close this. Keep that open. Close this one. Put some apps we're not using, just in case. Move this to the side. Move this to the other side. Backend Docker file. just straight Python 3.10. Backend README. Backend scripts, restart.sh, set e set x. Use Docker Compose watch. Instead of Docker Compose upd, you change it to Docker Compose watch. Using backend README. For example, the directory with the backend code is synchronized in the Docker container. Copying the code you change live to the directory inside the container. This allows you to test your changes right away. There's also a command override that runs fast API run reload instead of the default fast API run. Hello TT, welcome back. It's been a while. Hello, Aditya. I'm working on my scheduler project at the moment. a chronic dark mode user, it's okay. The only reason I'm using light mode is just for a bit of spice in my life. I can understand the chronic dark mode usage. Front-end biome. Yo. What are you working on right now? This is basically me trying to fix copy over code from the original repository into my repository for this specific template, because I'm missing some stuff that I didn't keep track of all the PRs correctly on. So I'm missing some PRs that I should have copied over to my repository, but I haven't yet. So I'm doing that now, right now at least. Shouldn't be bad. Frontend package.json. Yeah. Maybe that's what I was missing last time. Hello Prayash, how's life? Still studying, but doing this first for a bit while I refresh my mind. Oh yeah, nice. What festival? It's not Halloween, right? I see, Prayash. Lanterns. I see. Seems like a fun festival. I'm guessing it's like evening then, where you are, maybe? Or midday, maybe. Hey, Prayash, that's awesome to hear. Go have fun, man. it's like it started yesterday and it's currently 9:30 in the morning. We celebrate in the evening. I see. Yeah, man. That's crazy. Good amount of celebration, I guess. Hello, Akshay. absolute. Do you use some study technique like the Pomodoro one? Not really. I've tried it in the past, but I've never stuck with it, to be honest. So, yeah. You know, if we're talking about any particular study technique that I am currently using, it's probably just doing problems over looking at the theory, right? That's one method. That's one technique, study technique. Stack name. What is happening today only with white mode? It's not the only time, but yeah. Just keeping a white mode for some reason. I don't know. You know? I think I'll be done with looking at this stuff now. I've gotten through quite a bit, but there's a lot of bugs that I gotta figure out as well. So I'm gonna call it here for this. Just close it. Today was one of your most unproductive days ever because I just got caught up on writing the perfect notes. But yeah, rip. At least the notes look nice. Perhaps. Okay. There's no pure strategy equilibrium, and the mixed strategy is I don't think I understand that quite clearly. Regardless. I could even work on one more today after I've done some tutorial slides. So let's have a look here. These are all the different problem sets. Not bad. And this respective solution sets. I should be able to just download these then. I'm going to do some lecture harvesting. I'm going to do some solutions harvesting. Yeah, it was tough. I just have to remind myself the important things like actually practicing and studying the and applying the info. Yeah. It's yeah, it's challenging, right? But I think once you understand that things are meant to be messy, especially when you're studying, I think that'll free you from a lot of the tidiness burden. For me, at least, that's the case. How is this? This is confusing. Oh, you saw a mind for numbers on your reading list, on my reading list, and you picked it up today. Did I enjoy it? I think it was good, but I don't remember much of it anymore. The advice was, you know, the main takeaway for me at least was to do practice problems, right? That was the main takeaway for me, but I think Barbara Oakley, the one who writes the book, does empower you to think in a way that's right, I guess, in a sense. Not necessarily right, but a good approach. Problem set, solution set. I just need to upload the ones that are missing from here. I guess do it from Alacrity. Ten. 9, 8, so I'm guessing this was meant to be 7. solution set 7, solution set 8, solution set 9, 10, 11. Dude, how busy is the schedule? You're working and still taking classes, right? I'm mainly studying. Not working at the moment much. Right? I used to work quite a lot. I used to be like doing some freelance stuff. I used to actually work part-time. And then there was also a startup that I worked at, and that spread me pretty thin. And so now I'm complete opposite, where I'm literally doing no obligations but this. But study and building my own things. I know the title of this stream, basically. Cool, all of them added. Now all of these tutorial slides are going to be super helpful. Now arguably more helpful than the solution sets, so not going to worry too much there. You can delete these. And CS APA. So we don't got 10, we don't got 9, we don't have 8 or 7, and then 6, 5, 4, 3, 2, 1. We all have. So downloaded only 1, right? Yep. 10. You took pure math, right? How hard are those courses compared to CS? To me at least, they were much harder for me than CS was. We're talking like orders of magnitude 5 to 10. So one, 2, 3, 4, 5. Three, 4, 5, 6, 7, 8, 9, 10, 11. Ideally, what did I just hit? Okay. APA. If I practice these tutorial questions well, then I'm set, I think. It's a matter of having them set out in a way that I want to. Hey Jacob. All good, man. Hope it went well. I mean, I'm glad it helped me. I mean, I'm glad it helped you because, you know, that video I shared, that video specifically helped me a lot. So, yeah, good. Hope it goes well. Keep us updated. Key concepts: normal form, games, strategies, and equilibria. Okay, this is going to be useful for that question on game theory. So, single agent problems versus multi-agent. So, single agent problems, reward is dependent on our actions and the environment. Multi-agent problems, payoff/utility is dependent on our actions and the environment and other agents in the environment. Normal form games, non-sequential games, and extensive form games, sequential games. English auction, Dutch auction, and Vickery auctions. These are 3 different auctions, and you can think of them as mnemonics of up, down, and Vickery auction. I guess, you know, these problem statements, they will tell you how it's done, but starts with a low price increases the price, a high price decreases the price, public or private bidders known, no others bids. Private bidders doesn't know others bids. Pay the highest price, pay the highest price, pay the second highest price. So in an auction, English, Dutch, or Vickery, if A, B, or C, so 2, 3, or 4, 4 is the winner. 7 is the winner. B is the winner, only B, but B only pays $4. Still interesting. Strategies in Vickery auctions. Okay, so this is a problem. We have to practice. Are these all Vickery auctions? And there's mixed strategies. Okay. So consider a Vickery auction between 2 bidders, bidder A and bidder B, who each value the items at 50 and 51 respectively, assuming that the buyer has no reserve price. Are there weakly or strictly dominant strategies for these 2 bidders? If so, what are they? To simplify your analysis, assume that the bids can only be whole numbers between 49 and 52. Below is a normal form game matrix to represent the possible actions and outcome spaces. Bidder A, bidder B. Utility, how much the agent thinks the item's worth, how much the agent has to pay for the item. You think the car is worth 10k, you pay 10k to buy the car. Utility, value minus the pay, is 1k. Aim to have a high utility, and you pay 11k to buy the car, say. Then your utility becomes the value that you put on the car minus the amount that you have to pay, which is negative 1k, which means you want to avoid. So utility, payoff matrix, so okay. If that is the problem statement, you want to fill in the answers. I already did week 12 game theory somewhere, I know for a fact. Here, I think that's it. Yeah, this is it. So I'm gonna just use this instead of what I had before. And that means this one gets deleted. Don't know what this one is. Okay, I'm really just considering how can I best learn these slides, because I don't know if it'll be wise to just copy screenshots of this and then paste it and then try to do the problem yourself. I feel like that would take too long and is probably not our main purpose. You know, our main purpose here is to learn the content, not through these problems, but through exam problems. So I'm gonna say that I'm not going to copy these problems. I'm going to read the tutorial slides, make my own notes on those, which should be enough. Right? Make my own, I guess, thoughtful analysis, just like what I do with Leetcode problems, for those particular problems. Okay? How would that look? Well, let's have a look. So say for these Vickery auctions, see how they're done, understand that problem, and then just try to add that as like notes here for game theory. Okay. Now 4949. Y divided by 2. Is it because it's a tie? No, it's because you're just taking the average. But why take the average and not just the difference? Which is exactly what it says there. Okay, if it's a tie, then you would do the divided by 2. In that case, nobody wins any money. Is this right though? I'm gonna add these myself. $49.49, bit array is 50, 51, 0.5 and 1. Yeah, I'm fine. $50 becomes 0.5 and 0.5. 51 becomes 0.5 and 0. Right? Wait. 50 wins. Alright. 50 wins. It's gonna be 0. Sorry, it's going to be 1, and you can't divide by 0. But you don't get any value. Can we say that or not? Otherwise you would say what your value is. 49 minus 50. Yeah, it would be nearly 1, right? Double check. No. What would that be? And that's definitely more wrong than what I expected. Because 49, so 50 and 49, 50, A is the winner, A pays 49. The value minus the pay, and then UB gets nothing, so it's 0. Okay, so I can get that. I can understand that much. That becomes 0, but 50 and 51, is that not 1? Why is it 2? Are you dividing it by 2 as well there? You're doing 50 minus 49. So the value of A is the value minus the pay of the value, so 50 minus $49. It'd be bids 49 versus 50. How much? Okay, so utilities, how much the agent thinks the item is worth, how much the agent has to pay for the item. 49. 49. Bid values of 51, okay. So then what's 50 and 49 here? They value nope. Trying to understand, justify my understanding, justify it. All right, let me look at a different example. $50 and $49. 50 wins the bet. Sorry, A wins the bet. They value it at 50. So if they win the bet, against 49. Then the reward is 1. B bids 49. A is the winner. A pays 49. Oh, right, because this is Vickery. A gets 49. The value minus the pay. 50 minus 49. 1. Utility of B becomes 0 because they don't get anything. There is no change for them. Whereas if A bids 49 and B bids 49, then it's a tie. The utility of A is 50 minus 49. Because they would have to pay 49. And they would have to pay 51. Or that's what their value is at. So the utility of B is they would, get more value or more utility. More of a reward almost. By sheer fact that they value it higher. And they would have won. Okay. So if it was bidder A beats bidder B, bidder B beats bidder A, bidder B gets the 49. The 49 minus what they value it as is 2. So they would get 2. Okay, I get it. At 51, they would win the bid and get 0. This would also be 0, maybe. Alright, give me a sec. I'm gonna come back. I'm cooked, but I understand the problem. Evaluate at 51, they get 49. 49. This is 2 as well. 52 they bid, they get a 49. So it's 02 as well. And on the contrary, on the opposite, we have, so bidder A wins, has to pay 49. That means bidder A gets a value of 1, bidder B gets 0. Right, I think that's right. 1 and 0. 02, 02, 02. Okay, I'm gonna get this right. So this is gonna be the same all the way down. Then 50 and 50, then nobody wins. If nobody wins, what is their values? Well, 50 minus 50 is 0. So it might just be 0. And what, 50 and 51.5? Is that right? Yeah, okay. And then 51 and 51. So we're gonna say it's like 50 minus 51. It's negative 1. Negative 1. Negative 0.5. What we're thinking. Negative 0.5 to 51, 51, it means that we're gonna have 0. And then 52, that'll be negative 1. And 52, gonna be 0.5. Negative 0.5. I think negative 0.5, negative 5 and 0. Alright, good. And then these last 6. So if it's 51, bid 50, the value is 50, they get 0. 0. So it would be 0, 0. Zero, zero. So 0, 0. It'd be 50. It'd be 50, what? It'd be 52, they still get 50. So it's still 0, 0. If it's 51 and 50, it'd be 0, 0. If it's 52 and 50, oh wait, this would be 1, this would be 0 and 1. That would be wait. Yeah, no, that's right. $52 and 50. You take 50. 51 is what you value. One. Is that right? 0, 0, 0, 1, 0, 1, and 51 and 52. If A wins, you pay 51, then they get a negative 1 and 0. It'll be negative 1 and 0, and then 52 wins, that's beta B wins. Yeah, 51 is going to be 0, 0. -1, 0, 0, 0. Alright. We got there in the end. Strategies in victory auctions. So what is the dominant strategy? Okay, so here's the thing. I want to say, like, even after just reading all that, you know, the problem that I really face with, make sure that when you add values to a normal form game matrix, make sure that when you add values to a normal form game matrix, you ensure you understand the problem statement. In the case of the tute, this was understanding that victory bids are taking the value from the second bidder. As you know, emphasis on the second. Okay. Now, strategies in victory auctions. Now, what is the dominant strategy of A? So the weakly dominant strategy is the utility of choosing an action A is greater or equal to the utility of not choosing an action A. The utility of an action A is greater than the utility of not choosing an action A. In this case, what we have is, given some action, so the dominant strategy of A, which one is it? If bidder chose 49, it could be either 50, 51, and 52. If bidder chose 50, it could be either any of the bid or any of what bidder A did. If it was 51, then it would be only 50 and 51. And if it's 52, then it would be any one of those except 52. Now the problem is, so if bidder bids 49, what should A bid? Should bid for... should bid for... if B bids 51, if B bids 52, find the row that has all the circles. Row 50. Weakly or strongly? It's weakly. Utility of choosing an action is greater than or equal to the utility of not choosing an action A. Okay, so that makes sense. I need to remember that, so that is good. This slide is very good. So the difference between weakly and strongly dominated strategies can be understood in if this, then B would. If A would. If A chose da da da, then B would da da da. Right, this is the line of thinking. And you know, this is all part of game theory. Page this. Very good. Right? All part of that page. Right, and cool. Now, problem strategies and victory auctions. So what is the dominant strategy of B? Well, if bidder A chooses 49, B could be 2 at best. If it chose 50, it could be 1 at best. If it chose 51, it would be 0 at best. If it chose 52, it would be 0 at best. Then the weakly dominant strategy is 51. Cool. So that's also good. Now, equilibria in victory auctions. What is the equilibrium states in the simplified victory auction in problem 2? So the equilibrium states. Okay, equilibria, right? Equilibria is the problem that we also have come across. What is the equilibrium states? In the simplified victory auction in problem 2. So how do we determine that, right? Nash equilibrium states. So, Nash equilibrium states. They could be any of these but Y, right? Is it because they're any of the two circled values from before when we found them? Is that the case? Is that truly the case? Yes, it is. Yes, it is. So I can pick any of those Nash equilibria. So 49, 50. I bid 49 and 50. Is that a J or ID? I can't tell what that is. Okay, anyway, A bids 49. B bids 50. B can't change the strategy 50 to have a higher utility. Right. And if, it's if B bids 50. Right, if B bids 50. If B bids 50, A cannot change the strategy 49 to have a higher utility. Yeah. So that is valid. That is a valid understanding of the problem. Unfortunately, we have problems with identifying where I am. Doesn't matter. No, it doesn't. This is learning. This is good learning. Love how, you know, the only tool kind of for this study is Obsidian and a laptop. Like, this is peak. This is peak. Like, that's all I need at the moment. Reflection. I reflected on myself, and this is right. This is the right way to do things for this subject. Oh. Shoot. Oh, hello, George Val. I just realized something. Just random. But the difference between like a markdown note, markdown link, or a wiki link, say like doing something like this and then typing in your actual note, and versus doing a link like this, where you got, oh, you can't see. Hold on. I'm literally blocking it. And so is the text. If you can see right here, in the top of my head, those two different ways of linking. I'm wondering if Obsidian, when I move files that get linked in both of these ways, I'm wondering if only one of them will get updated. Like, I'm certain that this first one will get updated. I'm not sure if the second one will. And I've been using the second way for my notes, which RIP linking if that's the case. RIP my linking. Whatever. I won't think about it too much. Okay. Now problem 5, mixed strategy. So consider the following 2 games. And assume that you are playing as the row player. Okay. Mixed strategies. Okay, there was a problem 4 that I'll have a look at. George, so how would you check that? I actually don't know. Actually, yes I do. Just trial and error. Just move a file. See how it goes. Let me just do it. I'll just do it now, right? Why not? Alright, we create a new note. We create a new link. We create another new note. 1648. Now if we do 1648, that's the link with maybe hello world or markdown link versus, okay, sorry, that's not a markdown, wiki link. It's a wiki link versus a markdown link, hello world. So markdown link would be like this with hello with this title, I think. So if I do that, if I click this, it goes to this one, right? Let me see. Click this, it goes to the same one, yep. Okay, so both of them are there. Now if I move that one, which is here, if I move that to fleeting notes, for example. Now if I click this, okay, we're fine. If I click this, we're fine. Okay, either way it works, basically. Now the thing is though, what if I had one dash fleeting notes slash this? This would still reach the spot. However, now if I moved this to reference notes, one link gets updated. Sure, I see, it's just updates to what it was originally. Okay. So it does get updated in Obsidian. Okay. That means I can delete this from here. Oh, and it shows up as a red if it doesn't exist. I guess that's maybe the only difference. But not bad, not bad. Okay, so there was a problem 4 in this that wasn't covered. So using the concept introduced in lectures, you can argue that the weekly dominant strategy is for each bidder in a victory auction. Wait, what? Using the concepts introduced in lectures, can you argue that the weekly dominant strategy is for each bidder in a victory auction for n number of players and any value? Simplicity assumed that no two bidders have the same private value. In practice, this is not much more difficult than to reason about. Not much more difficult to reason about. I didn't even understand that question. So using the concepts introduced in lectures, can you argue that the weekly dominant strategy is for each bidder in a victory auction for n number of players and any value. In practice, this is not much more difficult to reason about. So you have n number of players. Can you argue the weakly dominant strategy for each bidder in a victory auction for n number of players and any value? I think that's just coming from the pattern that you saw here, which is $51, value is always 0, 50, the value is always 0. I think there's something to do, it's something to do with that possibly. The solutions tell that clearly the combination, oh wait. Assume that a player values the item at value V. Their bid B can be either equal to V, less than, or greater. If they decide to bid B is greater than V, then one of their three outcomes can occur. Another player bids higher than B. In this case, our player would have done just as well to bid V, because it would have lost anyway and received utility of 0. All other players bid less than B. In this case, our player would have done just as well to bid V. They would have won anyway and paid the next highest price. At least one other player bids B prime such that B is greater than B prime, which is greater than V. Now a player wins, but player B prime, which is more than it values the item, it pays B prime. Thus its utility is V minus B, which is less than 0. Bidding S and losing. Bidding S and losing. Slimar became made for underbidding with B prime such that B is greater than B prime is greater than B, thus wins the auction. Our players could have won the auction by bidding V instead and only paying B prime, thus gaining utility this. Okay. Damn, that's hard. It's hard. Tough. Real tough. Cool, I think. Good there. Alright, now mixed strategies. So consider the following two games and assume that you're playing as the row player. Note that the only difference between the two games is the payoff 320 and 44. Just by looking at the payoffs, try to guess which strategy you would choose in each game. Now calculate the mixed strategy that both players should play in both of these games. How close was your intuition to the mixed strategy that you calculated? Pure strategy, always select the same action every time, versus mixed strategy, select the action based on probability distribution. Good definitions, I will say. Good definitions. So you are the role player, you can choose action T or B. In game 1, you think you should choose T more often. In game 2, you think you should choose B more often. The reason is you have 360 versus 120, and you have 88 or 84 versus 120. That's what I'm thinking. In game 2, you think you should choose B more often. In game 1, you think you should choose A more often. But in B2, why? Why? Guess you don't get that much more. Yeah, that's the intuition, I guess. Okay. Well, the mixed strategies, so consider the following 2 games and assume you're playing. Your strategies again, so which action you should choose in game 1 and 2. So we said T and B. So the role player chooses T. The column player chooses R. Because if you know row players choosing T, then you would choose R. If the row player chooses, if the column player chooses R, then the row player will know to choose B. And if column knows that row player will choose B, then column player would choose left. And then when column player chooses left, the row player will choose T. Cyclic. So no pure strategy, Nash equilibrium. Because they're cyclic. Now consider a mixed strategy equilibrium. Note that okay. If you think about it, in the same way that you would do the problem you would circle, if you're the row player. Alright, say you're the row player. Oops. So if you're the row player versus the, let's do blue, column player. Or should we do green? Column player. Row player. So you would 320 if column player chooses L, column player chooses right, you would do 80. If as the row player you choose T, right, would choose R. So you would go like this. And then if row player chooses B, then L chooses, column player will choose L because that gives you the highest. Now, because nothing overlaps each other, then we know there is no Nash equilibrium. Mixed strategy. Which mixed strategy SKDA man, hey, this is for AI planning for autonomy. Specifically, I'm learning about game theory. So it's confusing because it's a matrix and all of these values could like be each other if you don't understand it well enough. So this is like pretty hard on my head at the moment. Mixed strategy, okay, let's see. So mixed strategy, determining a mixed strategy. So you select the action based on the probability distribution. Mixed strategy is a probability distribution and isn't the same action every time. Your strategy. Okay, so I think, right, that yeah, so thing is, what about game 2? So if row chooses true, you would choose 80. If row player says bottom, you would choose 80. Oh, it's the same thing, isn't it? I think I just realized. So we'd choose 44, and you would choose 80. All right. For row player, so still the same thing occurs. Okay, so I think that's fine. Do I need to say anything else to that though? No. Mixed strategy. Okay, you are the row player. Your opponent is the column player. Make the expected utility of the column player not dependent on Y. No difference between player L and R for the column player. Y equals L equals R. So this is a good question. How do you make sure you're doing the right thing? Forty times X plus 80 times 1 minus X. Yeah, okay. They're the same. So in game 1 you would do, if you are the column player, Y equals 1 on 8, Y equals 10 on 11. This just give you the equilibria. So, what is E in this case? Such that it does something to something. I need to look closely at what that equation is again. Extensive form games. Oh, here we go guys. This is gonna take forever to load because of these large files. This isn't even what I need, right? This is an extensive form game. We're still talking about normal form games at the moment. Expected utility. Okay, here's the thing, right? I think I did a good job. On this, and I'm gonna treat myself to doing more scheduler development a little bit. Need to shift my mind again. We'll come back to this. All right, we're working in light mode all day basically. But should we turn a dark mode now? Shall I turn a dark mode? I might. I mean, half dark mode, half not is kind of... This contrast might be too much for me. Having light and then dark, yeah. I mean, I know I can do this as well, actually. Let me try it. It half works. Unless I'm meant to refresh here. This page. No, it's still the same thing. I'm sure there's a way. I will search it up. Excalidraw PDF invert colors. August 1st. This was this year. Is this still an issue? It's still an open issue. When switching on Excalidraw, the color representation of images is off. Test the browser. Okay. Yeah, but that's not even the problem for me. I think this is way too complex. Meh, nah, I'm not gonna worry. We keep it in light mode. Alright. What's this? I thought you're the student rep. Okay, our CPU might go hectic. I'm gonna put a timer on this. I'm gonna put 20 minutes, 18 minutes. Inbox. Let's try and reach inbox 0. Maybe I can finish all these today. In these 20 minutes. Okay, that's actually good changes. I like it. Remove unnecessary comment. Ooh. I mean, this was ages ago, hey. Alright, we can mark this as done. I guess we don't use copier, so it doesn't matter here. Interesting. Hey, I'm almost done. Hmm. I could finish this all. That's 18 minutes. Still gonna do a little bit more. I'm really... Oh yeah, I want to do a little bit more here. Subham, have you checked M4 Max? I have. They do look pretty good, except we'll see if I'll get them or not. You know what I mean? Hello, Hasib. Which subject exam? This is gonna be... We got 2 exams coming up, AI Planning for Autonomy and Computer Vision. Those are the 2 exams coming up. Oof, some heavy subjects. They sound difficult, to say the least. this is slow now. For good reason. No. Yeah, I guess it doesn't matter, right? Don't need to be pedantic about it. It's good enough as is. And that's admin and items. Items will have to change this. So it's a refactor at the end of the day. Pagination. Damn, bruh. This is slow as hell. Damn. It's almost unbelievable how slow it is. Hold up. Alright, we're gonna close some tabs because this is just gonna take forever otherwise. Alright, that means the music's gonna go off for a bit. Okay, and then we would just reopen it. Pagination footer. Okay, well, I think I'll just pause for now. If I really want to do more, I can do more later. Alright, so we're just pausing that for now. Play some lo-fi music again. I'm gonna close these tabs. Yo, this is still loading pretty slowly. Alright, so we did game theory, week 11 tutorial. We did more scheduler development. Technically maintenance. But that's done. Now, I could watch another lecture, or I could just try the question again. Okay. So then maybe I don't do this. And then maybe this is something I do tomorrow as well. Yikes, man. Yikes. Yikes. Okay. Let's see. What can I say would I do? So I might practice exam question. Thing is, we got dinner now. I'll come back for a little bit more time just to attempt the practice exam question on game theory, and then I'll be done for the night. Alright, so the practice question again on game theory, I'm gonna do that tonight after I come back from eating dinner. Alright, so that is the plan, and then by then it'll probably be like 8 PM. Alright, so then this might just have to be done tomorrow. So considerations. We'll think about it. Alright, but for now let me go and eat. Alright, so I'll be back. I'm back. Okay. Time for the practice question. Let's see. I wanted to check something before that. I wonder, let me check my phone. Checking something real quick. Whatever. Is it the same? Looks similar. I think it's fine. Wind down from an hour from now. Void screens. Okay. Still fine. All right. Let's go. So. Pure strategy. So, if player 1 picks up, player 2 will pick 4. Okay. And we're saying player 2 is player 2. And if player 1 picks down, player 2 picks right. If, let's see, if I get rid of this, just consider, okay, green maybe we'll call it, player 1. If player 1 chooses L, then we go down. Player 2 chooses M, is down. Player 2 chooses right, we go 1. Now, since none of them overlap, there is no pure strategy equilibria. right from this no pure strategy equilibria exists. Cool. And so when doing the next step, you can directly cross out. Just like before, I guess. To know that what to do. So now there's a challenge question we can try. Alright, maybe I'll try. Two players A and B play the following game. First, A must choose in or out. A chooses out, the game ends. And the payoffs are A equal to B to 0. If B chooses in, then they play the following simultaneous move game. Draw the extended form tree for this game and calculate the equilibria of the extended form game. Note, to draw the tree you can use text format. Represents a true with root. Play two choices, move B and C. This might be a question that comes up in the exam realistically. So we need to think about it for a second. Maybe I'll just stand up. How does that even work? Can I be bothered? It would mean I have to understand what in the world is this question? These questions, man. Good questions nonetheless. But I am cooked thinking about these problems. I will maybe just pause it here. Give myself, I might as well just get up to date with the scheduler inbox. And then maybe we can merge and do some stuff there. Just because I am pretty good for the day. Just want to do a little bit more scheduler development now. Because why not? You know what I'm saying? Okay. Hello, Rawat G. Hello, hello. I almost butchered your name. Actually, I might have already. Actually, I'm sorry. Yeah, GG again. By the way, you are doing great work. Thanks, man. I hope so. I really hope so. I think I'm on the right path. Here we go. So this is where the backend Docker file got changed. So that brings it full circle now. For me at least. Ooh, did it really get overwritten that quickly? Okay, backend readme. So this one I'm fine with. Poetry lock got changed where you just remove, I'm guessing, poetry. Wait, poetry lock got completely removed. Alright. Right? It's completely gone, right? Oh, this file was deleted. Never mind, yeah. Okay. Pi project toml. UV lock is what is in its replacement. Copier. Don't need to worry about. Dev though. Backend UV lock is one of the things that I gotta commit. Alright, well let's have a look at the backend readme. Backend, yep. Now this is in the requirements. UV. docs.astral.sh/UV for Python package and environment management, and general workflow. By default, the dependencies are managed by UV, where you have UV, CI, go there and install it. Thing is, so if I go there, hello Shah Jalani. Good morning, good sir. An extremely fast Python package and project manager written in Rust. Ten to 100 times faster than pip. Install UV on our official standalone installer. And check the first steps or read on for a brief overview. Project management. Find Rust quite tough, to be honest. I feel like, because I haven't learnt it yet, it's probably going to be equally as tough for me as well. I've heard new paradigms, so you know. UV is going to be pretty sick to try and use. So console poetry install is actually just going to be UV sync. The virtual environment with source venv bin activate. Make sure your editor is using the correct Python virtual environment with the interpreter at backend dot venv bin python. Is this project on Rust? No. Well, not what I'm building, but UV is written in Rust. That's why it's so fast. Even the devs who are working on Rust aren't comfortable with it. I mean, I wouldn't be surprised. So the thing is, I'm copying and pasting this. I'm convinced that's fine. Now backend UV lock is just going to be I might as well just copy this file, alright, because you know, what if I mean, I might as well, okay, I will try and run it once. This command. Ooh. I can't. Okay, I won't. But I will copy and paste. UV.lock. Okay. That's a UV.lock. How many? 1,554? Development. Poetry. Using UV. UV run pre-commit install. This becomes UV. Using UV. It's the final change. Update labeler. I think I don't need this one. Refactor the API. Thanks for the interest. I see as lots of changes packed in a single PR. It would be better to separate each atomic suggestion in an independent PR that can be individually reviewed. I see a lot of the changes are new CRUD functions. An older version of this project has lots of them, and I actually did put a lot of effort into refactoring it to remove all the extra complexity. Also, the doc strings depend on the specific format. I would prefer to use what I use for fast API, and right now I'd rather not have doc strings in these functions yet. Also, separating models into files can lead to complex logic to handle imports, reference cyclic imports, etc. So I prefer to have the simplest structure possible and allow people to refactor and evolve as needed. You can read more about this in the SQL model docs. I'll pass on this one, but thanks for the effort. Well written, still regardless, but 59 file changes, like damn. My guy went all in. Justin P. Okay, mail catcher for sure. Yeah, this isn't included in the development docs. fix smoke show, check out files in CI. Smoke show. Handle non-exist user IDs. Improve backend test performance. Super user password, is that the case? Okay. Yes. Maybe. Doesn't matter. You can take that off. Some container versions in Docker. Carousel poster. Fine. Oh my god. This guy committed his .venv directory. Oh, at least that was a while ago. No, this was last week. Never mind. Some minor changes. You're not joking with these ones. These just get funnier. Oh. I mean, this is what happens if you go open source, I guess. Playwright, CI speed, sharding, parallel runs in Docker to use cache, use nvars. Interesting, so this is the playwright. Oh shoot. There's Docker compose, override. Front end env. You add that. Okay, this is pretty big. Let me go back. Better HTTP error codes for login endpoint. Maybe up to updating it. Okay, so anyway, this is what needs to be done. Okay, this will be the last changes. Playwright, I think I can just copy directly from the file. So let me close these files here. Okay, close them all. Playwright, copy, paste. Now we have master branch, but I'm calling it main. I don't think anything else differs. So even still, it doesn't matter for now. Test Docker Compose. You go to that file. So when you test Docker Compose, this is line 21. You add backend, front end, and adminer. And then you override. When you have an override, you add full playwright section in the override. Now this is at the very bottom of the override, I believe. Right after the networks. And indentation. Get rid of that. I think that's fine. Okay, that's done. The override's done. This is done. This is done. Frontend.env. So that means this env.example. Mail catcher host is equal to localhost 1080. Let me sit down. Front-end Docker file playwright. New file. Docker file playwright. Playwright config ts. Playwright config ts. If we view file, copy, paste, Yep, that removed, that added, that added. And there's no other changes there. Admin.tsx and item.tsx. Alright, well, we're gonna have to open those up. So this is in layout admin.tsx. 52. Okay. Prev is key string close bracket. I don't think it makes a difference. I guess it's fine as is. Layout.items. So 48. Prev, same thing. Okay, so now front end test. Reset password. Spec.ts. View file. Copy the entire file. Paste. Go back. Page go to, process env, mail catcher host, message. Same thing, mail catcher host, message. Okay. And alright, utils mail catcher. Keep on changing stuff for mail catcher here. Utils mail catcher. I want to go to the file directly. Let's copy it here. Should just see everything to be the same except for that one, which is true. And then lastly, ts config, which to me, I'm just going to copy this whole thing. ts.config. Where is it? ts. config.json. Sus. Why is that so different? Alright, shadcn. Alright, so we just do changes here. So 23, no fall through case switch, true. So this is a whole new line change. You can compare before and after just by looking at this. Basically, you include all TS files in source directory, include it in tests and playwright. Okay, and that's done. Alright, we're up to date. We're up to date, boys. Took us 3 months. But we're finally at the end. Now it's a matter of making sure everything in the actual repository is working as intended. Now, I'm pretty sure it won't be working as intended. Please look at all that. Look, playwright tests, I don't mind them not working. However, generate client, failing, input required, not supplied, so token, right? Now that is easily changeable. Generate client. Repo token, all right. How to create a repo scoped GitHub access token. I'd rather not do it this way. I'm pretty sure you can just check out the repository settings to find what we need. Deploy keys. Pages, code spaces, environments, webhooks, actions, rule sets, mod options, general. Not general. Deploy keys, maybe. Nah. So secrets and variables. Gotta be a secret. But I need a repository token. Should be able to get one somehow. Does it have to be specific to me? So repositories. Dev settings. Okay, this is taking a while to load. Password and authentication. Why is it taking a while to load actually? I don't have a reason. Alright, maybe we just don't worry about this for now. Come back to it. When we have a fresher mind, I might say. We might call it a day. That's not it. Nahi. Oh, personal access tokens. Fine-grained tokens. For quick access to GitHub API. Well, actually, I don't want to do this right now. Anyway, I'll call it a day though. I'll be done now. So Nahi, I'll be getting out of this chair and actually moving. But yeah, it's been good, guys. I did quite a lot that I wanted to do today, so I'm pretty happy with that. I'll worry about tomorrow. So we'll call it a day. Good night, guys. Good morning if it's still the morning or afternoon to use. But yeah, Nahi, no worries. I'll be here all the time. Thank you. I'll have a good night. All right. See you guys, and see you guys probably tomorrow. Peace.